Welcome to this online training describing the Arria SoC FPGA Hard Processor System, also known as the HPS Overview for Cyclone V and Arria 10 SoC FPGA features. By the end of this online training, the customer will be able to understand the key blocks of the Hard Processor System, HPS, on Arria SoC FPGAs. The objective of this training is to provide an overview of the SoC hardware and system architecture for Cyclone V and Arria 10, as well as Arm Cortex A9 HPS. The agenda will cover topics on the block diagram and HPS architecture. Let's now discuss in more detail the microprocessor unit, also known as the MPU. Here's a more detailed block diagram of the subsystem found in Cyclone V and Arria 10 devices. The portion in blue is the Hard Processor System, or HPS. It contains the dual-core processor, and each CPU has its own floating point unit, Neon coprocessor, and L1 caches. The processors share an L2 cache and a rich set of peripherals, including 2 triple-speed Ethernet ports, 2 USB on-the-go ports, interfaces to flash memory, general-purpose embedded peripherals such as UART, SPI, CAN, and I2C, and a shared multi-port front-end SDRAM controller that supports DDR2, DDR3, and LPDDR2, all with ECC. Dedicated fast-speed interfaces connect the HPS and FPGA fabric. The FPGA can also be directly connected to the SDRAM controller in the HPS. The processor can also directly access the FPGA configuration controller to configure the FPGA using software. The purple portion on the diagram represents the FPGA fabric, and the gray blocks represent additional hard IP functions available to your FPGA custom logic, including additional multi-port SDRAM controllers, PCI Express ports, and high-speed serial transceivers. This is the diagram of the Hard Processor System portion of Arria SoC devices. It consists of the multiprocessor unit along with many peripherals such as SDRAM controller, Ethernet MAC, DMA, flash controllers, USB, SPI, I2C, UARTs, and GPIOs. The microprocessor unit is indicated in the diagram. We'll talk about the features of the MPU subsystem, including the CPUs, Snoop control unit, and the L2 cache. The MPU subsystem contains many components. The first part is the MPU subsystem itself. It contains an Arm Cortex A9 MP core, a Level 2 cache, built-in debugging modules, and an accelerator coherency port, ACP, ID mapper to allow for cache coherency with all managers in the system, including the DMA, L3 managers such as Ethernet, FPGA peripherals, and the debug access port. Then within the MP core, it contains the following: dual Arm Cortex A9 processor cores, Snoop control unit, or SCU, with an accelerator coherency port, a global interrupt controller, or GIC, a global timer, private timers and watchdogs for each CPU core. Each core within the MP core contains an Arm Cortex A9 CPU, as well as a Neon SIMD vector coprocessor and a scalar floating point unit with up to double precision capabilities. Level 1 instruction and data caches and memory management unit, or MMU, also exist for each core. The Arm Cortex A9 is an application class processor, meaning it is tuned for throughput and not latency. Here is where it falls into the ARM product lineup in terms of performance and functionality. This device is compatible with Arria's Neos 5 processors IP for additional features on your SoC device and performance. In this block diagram, we are looking at the hierarchical view of the MPU subsystem. You should see that the Level 3 interconnect manager is connected to the MP core through the accelerator coherency port and the corresponding ID mapper. The Snoop control unit provides the cache's coherency between the ACP and the 2 Arm Cortex A9 cores. The Level 2 cache is shared by both CPUs, as well as any managers accessing memory through the accelerator coherency port. Finally, the L2 cache is then connected to the Level 3 interconnect, as well as the SDRAM controller. The HPS supports different memory views, which is the way each of the managers accesses subordinate peripherals and the SDRAM in the HPS, as well as the connected FPGA fabric. Each of the managers will see a view of the 4 GBs of memory. One of the views is directly from the Arm Cortex A9 MPU subsystem. This is a configurable view. There is a default configuration places the built-in boot ROM at address 0. SDRAM going from 1 MB to 3 GB, FPGA peripherals from 3 GB address and other peripherals above that. You have the option of remapping address 0 to the on-chip RAM if you need that, or you can also remap SDRAM to be located at address 0. And you can also float the SDRAM address space to include more than 3 GB worth of address space. Do note that if the on-chip RAM or boot ROM is mapped to address 0, the contents are also aliased in the peripheral memory region. For more information on remapping, go to the SoC Device Handbook. Work within your toolchain and operating system to utilize the hardware features of the MPU. For example, caches are enabled as a normal part of the boot process and are automatically used. We will now look at the System Memory Management Unit, also known as the SMMU, in more detail. Each CPU core contains its own memory management unit, and this MMU provides 3 main functions. First, it translates virtual addresses to physical address. It also provides memory protection, and it also assigns memory characteristics to pages. The translation is based on page tables that are stored in main memory. There is also what's called a translation look-aside buffer, or TLB, that acts kind of like a cache in between the page tables and the MMU itself. The page table consists of 2 main parts. The first part are the section descriptors, which describes a 1 or 16 megabytes block in memory. Then there are the page descriptors, which describe either 4 or 64 kilobytes blocks in main memory. The section descriptors point at page descriptor tables. So think of these as a 2-layer approach to chopping up the memory into small blocks. The page table is essentially used to map in virtual addresses to physical addresses. So typically user application code doesn't have direct access to the physical addresses, but instead the virtual addresses that would be provided by the OS through system calls. The translation look-aside buffer is broken down into 2 different levels. The first level contains the instruction and data micro TLBs, while the second level contains the main TLB. The micro TLB characteristics are 32 fully associative entries per micro TLB, 1 clock cycle per lookup, and if the entry is not found in the micro TLB, then it progresses on to the main TLB. The main TLB, which acts as a level 2 TLB, contains 128 two-way associative entries and 4 fully associative lockdown entries as well. It contains variable lookup latency, and misses cause the lookup to progress over into the main memory, which is also called table walking. The table walking is accelerated using the level 1 data cache as opposed to using software to perform the walks in main memory. We will now talk about the bridges in the HPS in more detail. The HPS contains 3 AXI bridges. The first one is called the FPGA to HPS, and this is used for managers implemented in the FPGA fabric to manage subordinates in the HPS block. There is also the HPS to FPGA bridge, which is for managers in the HPS block to manage subordinates that are in the FPGA fabric. There is also a third bridge called a lightweight HPS to FPGA bridge, and this is meant for managers in the HPS system to control mainly the CSR's registers integrated into the FPGA fabric. For example, you may have a PIO that you have implemented in the FPGA fabric, and instead of tying up the bandwidth of the HPS to FPGA bridge, you can connect it to the lightweight bridge instead. All 3 bridges provide their own clock crossing, so the FPGA ports are clocked independently of the HPS ports on the other side. They support asynchronous clock crossing, so that you can use any timing relationship want between these 2 different clock domains. In the case of the FPGA to HPS and HPS to FPGA bridges, they support variable data widths on the FPGA side. They can be configured to be 32, 64, or 128 bits wide on the FPGA side, while on the HPS side they are fixed at 64-bit and up half the processor frequency. to provide the most throughput possible. Normally, you would set up these bridges to be 128 bits wide so that you can saturate the 64-bit HPS side. The data width of the lightweight bridge is fixed at 32 bits on both the FPGA side and the HPS side. This lightweight interface does not support burst. Here is a block diagram that shows how these three bridges are integrated into the system. All three are connected to the Level 3 interconnect, while the lightweight bridge is also used to set up various functionalities within the other two bridges. All three bridges connect to the FPGA fabric, and as mentioned before, clock crossing is performed within the bridge itself. So you can use any clock that is available from the FPGA fabric, as well as clocks that are generated within the HPS block that are available to these bridges. At this point, you may be wondering why there are two different HPS to FPGA bridges. The reason for this, there is two types of traffic in the HPS block itself. You have slow CSR accesses to peripherals to read their status and control them, and you have faster accesses to things like memories and hardware accelerators. You will want to split this traffic into two different bridges, so that one does not impact the performance of the other. In terms of the CSR accesses that gets forwarded to the lightweight bridge, they are typically accessed as device memory. Device's memory accesses cannot be resized or merged by the bridges or the Level 3 interconnect. These accesses are typically 4 bytes or less, because they map into either reading from status registers or writing into control registers. Therefore, accesses to the lightweight bridge are typically used for short latency sensitive accesses. For example, clearing the interrupt in a peripheral that is implemented in the FPGA fabric, while the regular HPS to FPGA bridge, or as I call it the heavyweight bridge, is used for more bursting type traffic. For example, executing code that is within the FPGA fabric or triggering the DMA to move data back and forth to a hardware accelerator that's implemented inside the FPGA fabric. The HPS IP is offered in Quartus Prime software as a released IP. The simulation of the BFMs are limited to interface-only modeling, so the internals of the HPS are not modeled. In the Platform Designer System integration tool, if you generate a test bench or a simulation model for the system, the HPS component will be replaced by appropriate AXI BFMs at each of its bridges, a manager BFM for HPS to FPGA bridges, and subordinate BFM for the FPGA to HPS bridge. The AXI BFMs are provided by Mentor Graphics. See the Mentor AXI BFM user guide for more information and usage scenarios. The hardened memory controller in the HPS system supports DDR2 and 3, as well as low-power DDR to SDRAM on Cyclone V and Arria V devices. On Arria 10 devices, it supports DDR3, DDR4, and LPDDR3 memory components. The controller supports ECC, correcting single-bit error correction, as well as double-bit error detection. It uses write-backs to implement the ECC functionality. Whenever an error is detected, it can issue an interrupt to the MPU subsystem, allowing you to handle it however your program desires. Operation ordering is also supported for both command and data to improve the memory efficiency. The multi-port front-end portion of the SDRAM controller subsystem is scheduled on a per-port basis with an absolute priority set with up to 8 levels, and this is soft programmable. There is also a programmable relative weight per port, which is used as a tiebreaker in the case where two ports with the same absolute priority are waiting for access to the memory at the same time. After one of the multi-port front-end queues has been popped, the transaction progresses over to the single-port controller. This handles burst adaptation to ensure that unaligned bursts are efficiently accessed in the memory device. It also supports merging or chopping of a burst into bigger or smaller ones based on the memory burst length. The memory controller subsystem also supports various different levels of power management. It supports self-refresh and partial array self-refresh commands. It also supports power-down support for user-defined lengths of time or based on inactivity. There is also a deep power-down mode that is supported for low-power DDR devices. The SDRAM controller subsystem have AXI support, including AXI4 ordering rules. Memory protection is also supported, assuming you configure all of the ports interfacing with the FPGA fabric to use AXI. It also supports exclusive memory access as well. It can track up to 16 exclusive write operations which you use to perform mutually exclusive accesses, opposed to locking down the Level 3 interconnect, which is not supported by the Level 3 interconnect anyway or AXI 4 for that matter. Here, we are looking at the high-level block diagram of the SDRAM controller subsystem for Cyclone V and Arria V devices. It's made up of three main portions. There is the memory controller, which contains the multi-port front end, as well as the single-port controller. And then there's the DDR SDRAM PHY itself. There is a Level 4 peripheral bus connection into the SDRAM controller subsystem so that you can monitor the status of the controller as well as change settings on the fly. The external memory interface is shown on the right, and the various multi-port front-end connections are shown on the left. These include the connection from the Level 2 cache from the MPU subsystem, the Level 3 interconnect connection, and the various different ports that are exposed to the FPGA fabric. In Arria X SoC, the hard memory controller is actually located in the FPGA, but there is an SDRAM interconnect inside the hard processor system that contains connections from the MPU and Level 3, as well as the SDRAM scheduler and adapter. The controller, even though it is located in the FPGA, is considered for use by the HPS, so if FPGA managers need to access it, it needs to come through the SDRAM bridge into the SDRAM interconnect and then get access to the memory controller. There are three main types of interfaces between the FPGA fabric and the SDRAM controller subsystem. The first are the command ports, which include the read and write commands as well as the write response. Next, there are data ports, which are used for moving data back and forth between the FPGA and the HPS. Lastly, there is a sideband so that your FPGA fabric logic can control the refresh and power management built into the SDRAM controller. Since the data is handled independently of the commands, this allows multiple data ports to be gained together to form a wider interface. So, for example, if we wanted to implement a 256-bit wide interface into the SDRAM controller, we can consume a single command port, 4 read data ports and 4 write data ports. This means that we would be consuming all of the multi-port front-end ports at this point. If you don't need such a wide interface, then what you can do is use multiple command ports and use narrower data ports. You can also possibly mix and match Avalon and AXI interfaces for 28 nanometer devices in the multi-port front end. Just keep in mind that when you use AXI for each AXI port, you are going to consume 2 command ports. Here is a block diagram showing the SDRAM controller logic. This is the single port controller connected to the multi-port front end. The multi-port front end exposes read and write data independent of each other, and it also exposes the command port as well. The command port is what is responsible for issuing the write acknowledgements. For read acknowledgements, the read data is the acknowledgement, so it is not necessary to have an included read acknowledge. Another thing for Avalon users to consider is that it does not support write acknowledgements, mainly because it does not support posted writes. So if you make use of Avalon interfaces for the multi-port front end, you may want to consider performing readback verifies to ensure that write was successful. Of course, you could always consider moving on to using AXI interfaces, which do support posted writes. Unlike the other hard controllers that are built into traditional FPGA families, the Cyclone V and Arria V memory controller that is built into the HPS system relies on the MPU subsystem to initialize and calibrate the memory interface. The MPU is used to program the I/O scan chain bit for doing things like changing the voltage or delay chain settings. It is also used for programming the memory controller settings, such as the width and the timing, which is typically known at FPGA compile time. The SDRAM controller subsystem has support for cold and warm resets. In the case of a cold reset, the memory state is destroyed because the memory controller is put in a full reset and refreshes won't occur during this time. So, after a cold reset, full initialization and calibration will be necessary. In the case of a warm reset, the memory will continue to be refreshed by the memory controller, so the initialization and calibration steps will be skipped by the boot process. There are 8 levels of absolute priority that are software programmable for each port. 7 represents the highest priority value and thus the highest priority that you can assign to any port. When two ports compete for the memory at the same time, the higher absolute priority always wins over the lower priority port. Now, in the case of a tie, the scheduler will use the port weight that is assigned to each port. The scheduler uses a modified deficit round-robin scheme to schedule between these two ports of equal absolute priority. What this modified deficit round-robin scheme does is essentially smooths out the scheduling access pattern from the multiple ports that are coming in. This is a little different than the traditional weighted round-robin scheme that you might be familiar with. After the multi-port front-end scheduling is complete and one of the transactions is committed to the single-port controller, which then buffers the accesses and dispatches them based on the memory device's burst length. The MPFE priority is used to ensure that the bandwidth of the off-chip memory devices is most efficiently utilized. The burst scheduler favors read transactions over writes. The reason for this is that read transactions, especially from the MPU subsystem, are very latency sensitive, whereas write transactions, in most cases, do not care about latency. In the case of a burst scheduling tie, older transactions are favored over newer ones. This is to minimize the latency as much as possible. In order for an older transaction to be scheduled over a newer one, it also has to be the same type of access so that you don't ping-pong back and forth between read and write accesses, causing additional memory inefficiencies. We will now briefly discuss on-chip ROM features. The on-chip ROM, or sometimes called boot ROM, can operate at the clock speed of the L3 interconnect. This is the memory that gets accessed after a reset. The contents of the on-chip ROM is pre-programmed by Altera to contain the initial bootloader. The on-chip RAM is used by the primary bootloader as a scratch pad memory and can be used to store and run the first stage bootloader and possibly user bootloader. It operates at speeds up to that of the L3 interconnect and supports ECC as well. It supports single-bit correction, double-bit detection, and you can test if your software handles bit errors correctly. We will now discuss flash interfaces and peripherals. Quad SPI flash is a NOR flash with an SPI interface. It has a multi-I/O protocol, meaning that it can have a single SPI, dual SPI, or quad SPI interface. Essentially, the data bus is either 1 bit, 2 bits, or 4 bits. The HPS block has a single quad SPI controller. This controller supports up to 4 device selects, so meaning you can have up to 4 quad SPI devices. It also supports indirect and direct accesses, as well as execute in place. The controller supports quad SPI with either single, dual, or quad IOs, so the data bus can be 1, 2, or 4, as we said earlier. There is also a programmable write protected region, and it has DMA sideband signals for the external DMA. On this diagram, you see how the QSPI flash controller is connected to the rest of the HPS. On the left, it can perform a peripheral request to the DMA and communicate with System Manager regarding ECC through interrupts. It is connected directly to the Level 3 Interconnect Subordinate Interface for fast data movement. There's a Register Subordinate Interface that accesses from the Level 4 bus, and finally it can connect to the flash devices through a SPI PHY. The Quad SPI flash controller supports both direct and indirect accesses. Direct access is nothing more than a manager performing a read or write that then triggers a read or write to the flash. The manager will then be throttled while the read or write burst is being carried out. The software needs to configure the Quad SPI controller for optimal performance. However, basic reads and writes can be supported on power up. The Quad SPI controller also supports execute in place. This puts the flash in a read-only mode, so it lowers the command overhead by removing the fact that you can't do writes anymore. This isn't enabled on power up because the setup is device dependent, so the software will need to configure the Quad SPI controller before execute in place could be used. The Quad SPI controller also supports indirect accesses. This allows the Quad SPI controller to store read and write data into the SRAM buffer inside the controller. This gives you the capability of not throttling your managers while you're trying to do transactions, because in this mode the data is buffered and the buffer reaches certain level, it will trigger the manager signaling there's enough data to be transferred efficiently. To use this, you will need to set up the quad SPI prior to the transaction. The NAND flash cells are 60% smaller than NOR flash cells, that allows for higher densities at a lower cost. Because of this, you'll see this memory used more when you have larger memory requirements. The NAND flash controller supports a single 8 NAND flash device, or a single 16 NAND flash device on Arria 10 SoC. It also has an internal DMA, a bootstrap interface to the system manager, that allows the system manager to configure it during the boot process. It also has programmable ECC sector size, programmable access timing, and pipeline read-ahead and write commands. Here's the diagram of the NAND controller. It is connected to the Level 3 interconnect with a DMA manager interface, a command and data subordinate interface, and a register subordinate interface. It can trigger ECC interrupts to the system manager, as well as interrupt the MPU subsystem. Through the sequencer status module, it is connected to the NAND devices themselves. The single SDMMC host controller from Synopsys supports multiple standard card types listed here. Here you see how the SDMMC is laid out and how it connects with the HPS. The bus interface unit, which contains the DMA, is connected with the L3 interconnect through a manager interface that reads and writes data. There's also a subordinate interface for CSR access from the L4 bus. Finally, there's interrupts to the MPU. On the device side, the card interface unit connects to the I/O pins. Here are some examples on the SD use cases. Here is the same for MNC use cases as a reference. There are 2 Ethernet MAC in Cyclone V and Arria V families and 3 in Arria 10 SoC. The Ethernet MAC controllers with the HPS are standard compliant and support different Ethernet speeds, as well as full and half duplex modes. They support IEEE 1588 precision network clock synchronization, as well as energy-efficient Ethernet and VLAN tag detection. Here are some more features of the Ethernet MAC controllers. Here's how the eMACs integrate with the HPS. Each eMAC has an L3 manager interface that the eMAC DMA can access. It also has an L4 subordinate interface, where you access the control and status registers. It has an interface to the IEEE 1588, or the Precision Time Protocol, and this allows it to be shared with other IP such as CAN or the FPGA. For the PHY interface, the Ethernet MAC cores supports ARM2 or RGM2 natively directly through the HPS I/O. However, if you want to, it also supports GM2 through the FPGA fabric. They also support multiple PHY management schemes, so you can either use MDIO or I2C for your PHY management interfaces. So here, we'll go into the IEEE 1588 details. It's a precision time protocol, and we provide a resolution of up to 1 microsecond. It's used for network clock synchronization, providing multicast messages to get all the devices in a particular network, synchronized on the same clock. Each eMAC has a timestamp interface, and the MPU can use it to maintain synchronization between the time counters internal to the MACs. There is hardware support for timestamp management, so that on receipt or transmission of a frame, they are timestamped. This information can be shared with other peripherals, such as a CAN or other eMAC cores in the FPGA. These features do require a software stack to support them. The Ethernet MAC cores also have integrated DMA with a 32-bit AXI interface. They have programmable burst sizes for optimal bus utilization and separate transmit and receive engines for sending and receiving data. It supports byte-aligned addressing mode for data buffering, have a dual buffer mode so you can either do ring or linked list descriptor chaining, and descriptors can each transfer up to 8 kilobytes of data. USB on the go is a standard that essentially gives USB devices a dual role capability. It allows them to either be a device or a host. This enables point-to-point connections without the use of a PC. So, when 2 devices with on-the-go are connected, they determine who's the host and who's the device, and if needed, these roles can be reversed after they are connected. This gives the capability for HPS to host mode. You can, for example, plug a memory stick into the USB on the go, and then the MPU will be able to read the memory stick. The device mode can take the HPS or the SoC device and use USB on the go to plug it into a computer, and that computer then can treat the HPS as a memory device and read its file system. There are two USB on-the-go controllers in the HPS block. They support 3 different speeds. The USB on-the-go controller also has integrated DMA and supports all types of USB transfers. This is the USB on-the-go controller block diagram. You can see it is connected both by a manager interface and subordinate interface to the L3 interconnect, and the ULPI-PHY interface connects it to the external USB transceivers. Here are some more features of the USB on-the-go controllers. There are 3 USB on-the-go protocols. The first one is the Session Request Protocol. As seen here, it allows a B device to request the A device to turn on the power supply to the USB interface and start a session. The next protocol is the Host Negotiation Protocol. It allows the host function to be transferred between 2 directly connected on-the-go devices and eliminates the need for a user to switch the cable connections in order to allow a change in control of communication between the devices. The third protocol is the Attach Detection Protocol. It is an SRP-capable targeted host or peripheral-only B device to detect when a remote device has been attached or detached when VBus is not present. An external controller is required to support this. There are 2 CAN controllers on the HPS in devices that have them. These are designed using the Bosch IP and are only supported for Cyclone V SoC devices in the industrial and automotive speed grades. They support 128 message objects and have a programmable FIFO mode for message objects. They support automatic transmission and also have flow control signals for an external DMA controller. There are 4 SPI controllers on the HPS. 2 are dedicated as managers and 2 are dedicated subordinates. The SPI manager supports RxD sample delay, so this allows you to delay the receive input up to 4 clock cycles for better sampling. The SPI manager also supports up to 4 subordinate select signals. Both the SPI manager and SPI subordinate support external DMA controllers using flow control. Here's the block diagram for the SPI controller. The subordinate interface for both the SPI managers and subordinates come from the L4 peripheral bus. On the left are the actual manager and subordinate interfaces. On the right are dedicated interfaces to the HPS, including interrupts to the MPU and a DMA request interface to the HPS DMA controller. The HPS block has 4 I2C controllers on Cyclone V or Arria 5 devices and 5 on Arria 10 devices. 2 of these are general purpose only, while the others can also be used with the Ethernet transceiver control interfaces. However, if you're not using the Ethernet MACs, then you could be able to use these as general purpose also. The I2C controllers support both manager and subordinate operations and support 2 speeds, standard and fast. They support mixed read and write combined format transactions, as well as bulk transmit mode. The I2C controllers handle bit and byte weighting at all bus speeds. They also support DMA controller interface with the HPS DMA. Lastly, they have both a 64-byte receive and transmit FIFO. Here's the block diagram for the I2C controller. The top left contains the actual 2-wire I2C interface. On the right are IRQ to the MPU and the DMA request interface, while the control and status subordinates are available on the L4 peripheral bus. Here's the way general-purpose I/Os are implemented in the HPS. These do not include the 32 inputs and 32 outputs that are implemented by the FPGA manager. There are 3 general-purpose I/O interfaces implemented in each of our SoCs. They support digital debounce and configurable interrupt mode, so they can interrupt the MPU. The GPIO pins are shared with other HPS peripherals, so they can be only used if other HPS peripherals do not use them. For the different devices, here are how the GPIOs are laid out. In Arria 5 and Cyclone V SoCs, there are 85 available GPIO pins. 71 of these GPIO ports can be either used as an input or an output, while 14 of these general-purpose I/O ports are input only because they are shared with the HPS DDR controller. The three interfaces are implemented as shown. One module for GPIO 28 to 0, another for 57 to 29, and the third for 70 to 58, as well as the 14 input-only pins. In Arria 10 SoCs, there are up to 62 pins available. GPIOs 61 to 48 are implemented with one interface module, and they are HPS-dedicated IOs. The pins assigned to the other two GPIO interface modules, 47 to 24 and 23 to 0, are implemented using shared IOs. Shared IOs are actually located in the FPGA and can be used by generic FPGA logic. The DMA can handle the data transfer between memory-mapped peripherals and memories, offloading this work from the MPU subsystem. This is a microcoded architecture. It can be used for various types of transfers, such as memory to memory, memory to peripheral, peripheral to memory, or scatter-gather. The DMA supports up to 8 logical DMA channels, each one having its own thread. There's also an additional thread for management. The DMA has dedicated support for trust zone, with separate subordinate interfaces for secure and non-secure control status register accesses. Here's the diagram of the DMA as well as how it's connected in the HPS. On the left, you can see the Fast AXI Data Manager interface is connected to the Level 3 interconnect. The control secure and non-secure subordinate interfaces are connected to the Level 4 bus. Inside the DMA, there's an instruction execution engine that handles instructions from the 8 logical threads and the shared multi-FIFO, which can also handle ECCs. The DMA controller supports a 64-bit data path with burst support to give you very fast data access. Each thread is assigned its own AXI ID, where the channel number becomes the AXI ID, from 0 to 7, during data load and store. The manager thread code will use an ID of 8. There are connections for flow control to the DMA from peripherals that don't have their own DMA, which allow these peripherals to request and acknowledge transfers. Most peripherals require 2 interfaces, one for the receive and one for transmit. The peripherals can request either a single or a burst transfer. The DMA controller supports 32 of these flow control signals. On this slide, you can see how they're allocated between the peripherals. For example, there are 4 for the FPGA fabric and 4 that are shared between the FPGA fabric and CAN controllers if the CAN controllers exist, 8 for the I2C controllers, 8 for the SPI controllers, and so on, as listed here. There's also support for conditional code execution based on the peripheral request type. The HPS debug is comprised of many Arm core site components that can perform debug-related tasks. We'll go over each one and their capabilities in this presentation. The first component we'll talk about is the debug access port. It allows the debugger to access the core site components and system resources inside the HPS. The debug APB is the advanced peripheral bus connected to the debug port that is used to access the Arm core site components. It also has an AMBA AHB manager, which allows the debug access port to manage the subordinate resources so that it can read memory contents and control status registers. The AMBA AP subordinate allows other managers to access the debug access port and get the same information that the debug access port has access to. The debug access port only supports JTAG on the HPS and does not support serial wire. The system trace macrocell allows managers to post messages into the trace stream, and this can either be done by AMBA AXI subordinate port or by the event interface. Now, there are 32 event signals. 28 of these are coming from the FPGA and 4 are coming from the cross-triggering interface. There's also a timestamp generator, so these messages can be time-stamped upon arrival. The SDRAM allows, for example, for you to insert hardware events into the program trace and correlate them with the software execution. The program trace macrocell performs real-time instruction flow tracing for each one of the Arm Cortex A9 cores. It can generate the program trace information that gets stored in the trace buffer. This allows trace tools to reconstruct the execution flow, and you will be able to use this information to profile as well as to correlate between programs and other events and programs running on another core. The funnel will take traces from 3 sources: the program trace macro cells of CPU 0 and 1, as well as the system trace macro cell, and then it will route it to trace memory. You have 3 trace memory options. With the embedded trace FIFO option, you can use on-chip memory for storage, or you can use it as a buffer between the funnel and other memory. The other memory option is the embedded trace router, which can route the trace information and store it in any available memory in the HPS system. Or you configure the routing to use Trace Port Interface Unit, which allows the trace to be either ported off-chip with an 8-bit interface or to the FPGA with a 32-bit interface. This is used usually as a connection to dedicated debug hardware. The cross-trigger capability allows the software in the HPS and FPGA hardware to correlate debugging effort. For example, you can have the FPGA hardware cause a software processor stop, or you can have the software debugger cause a hardware signal. There are 2 components for this. There is the cross-trigger interface, which is used to receive and send triggers. There are several CTIs in the HPS, one for the FPGA, one for debug components, and one each at the processors. The cross-trigger interfaces are connected via the cross-trigger matrix, which then route the cross-trigger signal to the appropriate destination. Here is a list of available resources. To learn more, visit our website, where you can search for additional documentation. This course gave an overview of an SoC block diagram for Cyclone V and Arria SoC FPGAs. Then, to understand the architecture for the HPS, we covered several topics: the Microprocessor Subsystem, the SMMU, the bridges and their functionality, the on-chip ROM and flash interfaces. Finally, we covered also peripherals and their protocols, capabilities, and manufacturers. The Altera training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We welcome any feedback you may have. Thank you for attending today's training.